people that we really enjoy seeing around the department each day. And this lecture was put together by his students who organized the fellowship in his name, which I think makes it extra special. And he has a history of a lot of really great outreach for geography. So I think it's really fitting that we use this time with Malcolm to get together and hear from speakers. Malcolm, are you coming up?
No.
Okay. Sorry, I thought you were. Okay, well then come on up here with me, Dr. Batty. So then it's also my pleasure to welcome and introduce our speaker. So Mike Batty, he's visiting us from the University College London, where he is the Bartlett Professor of Planning. And he's also chair of the Center of Advanced Spatial Analysis. He's worked on computer models of cities and their visualization since 1970, and has worked on a range of things around the complexity of cities and using quantitative modeling approaches to understand them. His new book that just came out called The Futures of Cities was published in late 2018, and I got an email via Dean Wentz from Michael Crow with a picture of the book that he'd seen on Twitter, and he said, please get him here to come and visit. And so that is how we got here. But I also have, though this is actually the first time I've met Dr. Batty, I have this connection to him, because when I was interviewing for the job here, I was doing all kinds of searching on what was going on, and your Smart Cities course came up. And it seemed like the right thing to integrate geography and planning in our school. So I wrote this vision statement about how I was going to come here and we were going to do smart cities. But it was really based off that lecture that you were giving here. So it's my pleasure to welcome him, and we look forward to your talk.
Okay, thanks very much, Tristlyn. Yes, I mean, Tristlyn called me, as she said, and asked me if I'd like to come over and give this lecture, and I'm very pleased to do so. But she also said that Michael Crow had sort of motivated to some extent. Anyway, I went to see Michael Crow about an hour ago with Libby, and he had a copy of my book, which is called Inventing Future Cities. MIT Press came out at the end of last year. He didn't only have one copy of my book, he said he bought 100, and he gives it away. He likes the title. So anyway, this is the man who runs the university, basically. We had a very nice chat and so on, quite knowledgeable about cities in this particular context. So anyway, I have some quite strong links to ASU, I suppose, insofar as we have any links to universities other than the ones that we belong to. I have strong links to ASU. I first came here in the year 2000 to a meeting that Subra, who was in the planning school, organized on environmental and urban land use transport models. And in fact, on that meeting in something like April 2000, I think, I didn't really have any connection with geography at all, in the sense that I didn't really know people in geography in that context. It was only when Paul Torrens, who was my ex-PhD student from CASA, came to work here that I actually built the links, really. And over the last 6, 7, well, maybe 8 or 9 years, in fact, I've come about 4 or 5 times and given a 1-credit course, a 2-week course consisting of 6 lectures, Mondays, Wednesdays, and Fridays, Monday, Wednesday, Friday. I don't know what you can do with 1 credit if you've ever attended that course. It doesn't seem to kind of add up to any kind of degree at any particular point. But nevertheless, I was very pleased to give that, and I talked about smart cities and 1 or 2 other things. Okay, now, thank you to Malcolm for this lecture. I've not actually met Malcolm until tonight, although I have met him in the sense that I've seen him in the corridors, basically. And, you know, when you're a visitor, in a way, you don't really kind of, you can't really break the ice. But I'd seen Malcolm around a lot, so it was a delight to hear tonight that you had endowed a lecture for all his efforts over the years. So thank you, Malcolm, and I hope that you'll be around for many years to, this is the 18th annual lecture. Let's hope we get to the 28th or the 38th annual lecture. If you reach the 38th, then that'll be great. Okay. Okay, I'm going to talk about using simulation to explore and invent the future city. So what I'm going to talk about is really the following. I'm going to begin by saying something about prediction and about invention. And one of the kind of key themes in this lecture is the notion that we are extremely bad at predicting virtually anything. We're organized around this notion that we learn in school, basically, in high schools and so on, before we come to universities, that science is all about prediction. Now, I think that model is changing very rapidly at the moment. I don't think that science is really about prediction anymore. It's about explanation of a kind, and it's about rigor of a kind, but we'll see in our particular context how difficult it is to think about prediction. To some extent, in terms of cities, we're very bad at predicting the future in that sense, and there are many, many examples of this. But at the same time, in cities are all about what we invent, in a sense. Most of what we see around us is actually invented by ourselves in that sense. So if it's not about prediction, it's still about invention. And one of the kind of conundrums in all of this is that if we can't predict, we can't actually predict what we're going to invent in that sense. So that's really the one of the kind of themes. Okay, now I'm going to spend about 5 minutes or so talking a little bit more about prediction, and then I'm going to just briefly say something thinking about cities. In a sense, I'm going to make the assumption that cities are complex systems. They're really built from the ground up. They're not imposed in any way. Most of what we see in cities is the product of millions and millions of decisions that are, in some sense, quasi-independent of one another in that particular context, but nevertheless, we do get sort of emergent order in a sense. And one of the kind of key issues at the present time is that now cities are all global, and they sort of defy definition in that sense. So not only are we not able to predict in some sense, they also defy definition. Where does a city begin and where does it end? Even in a narrow spatial context, that's really quite a major problem. I'm then going to talk very briefly, a couple of minutes, on high frequency and low frequency cities. That one of the things that's come onto the agenda in the last 10 or 15 years is a concern for what you might call the high frequency city. This is the 24-hour city. As opposed to most of our thinking about cities, that's really over the longer term. Open a book on urban geography or urban and regional science, etc., things of that sort, and you find that most of what we've thought about in terms of cities in the past has been how cities evolve over quite long periods of time. Most of our thinking about cities is in this context. Certainly years, if not decades and so on, if not kind of even longer periods than that. But the high-frequency city has come massively onto the agenda, largely because we've, for the first time, begun to embed measurement devices into the city that are actually producing data. So the high-frequency city is all about the kind of data that we're generating in a continuing context, real-time stream data, basically. So I'm going to make this distinction between the two of them because prediction pertains to any of these kind of dynamics, etc. So a couple of my examples will be really about the high-frequency city, and the other examples will be about the low-frequency city. So what I want to do is to sketch the limits to prediction with respect to 4 examples. Now, my first example is on short-term prediction. I'm going to tell you a little bit about our transit and real-time stream data, our Oyster Card project, basically. That's essentially a project of taking big data from a system that is highly controlled in terms of 80-90% of people using the system are using smart cards to actually transit in some particular way, and to look at the kind of issues related to prediction in this very short-term context, predicting what might happen over a question of, well, not so much seconds, but certainly minutes, if not hours, in this particular context, in this narrow context. Then I want to talk about predictions that we cannot validate. I'll tell you a little bit about a project we're looking at in London, which is looking at Airbnb and how that's impacting on the housing market and the kind of tensions that really come from that. And then I want to look, my third example is going to be what we call data-driven flow models. It's really about building models at very near the data. It's about using the data, if you like, to predict. It's really, in some sense, saying that most of what we know about the future is probably contained in the present in this context. So why don't we actually take that as given and build models that are very close to the data? So that's what we call really data-driven models. And the models I'll be talking about are flow models in that sense, movement models. And then my biggest example, and I'll probably spend about a third of the lecture on this, I'm going to talk at longer term prediction. I'm going to tell you about this model that we're building for England, Scotland and Wales, which we call the Quant Model. It's essentially a land use transportation model. It's a spatial interaction model, and it works for Britain, basically. We divided Britain into something in the order of nearly 10,000 zones, basically. It's a model that actually sits out there on the web. You can actually access it on your phone. I'll give you the web address. I don't recommend that you access it on your phone because it's really very, very much a prototype in a sense, and the graphics aren't very good on the phone, but it's a model that's really designed for anyone, anytime, anywhere. And we've moved it from the desktop to the web so that people can get access to it. Anybody who looks at the kind of thing in the model in an informed way, it's really designed to look at large-scale impacts. The reason why we've built it for the UK, or not the UK, I should say Britain, I have to make this distinction. Northern Ireland is not part of it because there's a big sea between the island of Britain, Great Britain that is, and Northern Ireland. So it's England, Scotland and Wales. And for a long time, until about 3 or 4 months ago, we just had England and Wales. We've recently added Scotland. In deference to you and your wife, Stuart, we've added Scotland in that context. But it's largely because Scotland has a different administrative system, and the census data in Scotland is organised slightly differently from England and Wales, and it's done by the Scottish Registrar General, basically, as opposed to the Office of National Statistics, which is England and Wales. Okay, more of that later. And then really I'll try and sum up and talk about, we're really just at the beginning about thinking about models in terms of how good they predict. So let me say a few things about prediction. The key argument, I think, is that most systems across all the sciences, it's really only possible to predict within very strict limits, etc. An extreme version of this is that we can't predict at all in some senses. Now, we've got enough evidence now to show that most of our predictions are flawed in some way. They're very badly flawed if we actually step outside these rather narrow limits, etc. Now, there's a host of evidence which actually suggests this is the case. You only have to have lived through the last 10 years since the Great Recession in this particular context to know about the difficulties of prediction in terms of the economy in that context. You only have to look around here in Tempe. I was surprised. I've not been here for about 4 or 5 years. I was quite surprised at the buildings that have gone up on University Drive, basically, that the House of Tricks seem now to be separated completely. The first time I came here in the year 2000, basically, you could walk from the School of Design right across some wasteland, basically, to the House of Tricks, but now it's kind of been blocked off by a massive building. The interesting thing was that in 2010, when I was here, those 2 towers in downtown Tempe, which are residential towers, had actually stopped. They'd got to the sort of 2nd or 3rd story and stopped because of the Great Recession at that point. So there's some very interesting issues about our inability to predict in this particular context. Now, all of what I've been saying is pretty obvious. We're not magicians and we can't predict the future. And the future's largely unknowable, I think, because we tend to invent it ourselves. And as I said right at the beginning, that we invent it. We don't necessarily invent it as individuals, maybe collectives in some sense, agencies and so on. But it doesn't mean that we actually invent a better future from the present in this particular context. That in some senses, this is the conundrum I'm dealing with. And if we can't predict the future, then we can't predict what we might invent. And this is what I call the double bind of prediction in this context. Now, all is not lost in this context because we still have to predict. We want to predict in the sense that we need to predict to be able to actually exercise some degree of control over the future, in a sense. So there's lots of caveats when it comes to prediction in this context. And we clearly need a science of prediction. We don't even have a good catalogue of successes and failures in that sense. We're not good at actually looking at the past and documenting it in such a way and working out whether it's a question of success or failure, even within the narrow limits we set ourselves. And even that is problematic because, as we know, in some senses, our concept of failure and success actually changes. It's not invariant in some respects. We tend to resort to simple assumptions, which are wrong most of the time. For example, one of the assumptions might be we're able to predict better in the very short term on the assumption that bad things happen in the long term. So this is a widely held assumption that we can predict tomorrow, but we can't predict a year's time or 10 years' time or 100 years' time in some sense. And that, to some extent, is completely incorrect. It's the inductive fallacy. Bertrand Russell had this famous story about the inductivist turkey, right? Now, the inductivist turkey is an excellent example of thinking about the short term and the inability to predict in the short term. On the first day at the turkey farm, the turkey said to itself, or him or herself basically, it said a nice meal was served up for the turkey, so the turkey ate the meal. 24 hours later, another meal was served up to the turkey. So day after day, the turkey was served a nice, satisfying meal, and it got fatter. And eventually, the turkey figured out that every day he would get a nice, fat meal in this context, until, of course, Christmas Day arrived, and the throat was cut, and he found himself up on the Christmas dinner table in that context. So the tale of the inductivist turkey is the inductivist fallacy. Things may happen and seem to be predictable until some event, black swan event, etc. All swans were white until they discovered Australia, and black swans appeared in that particular context. So this is the inductivist fallacy. This is the reason why scientific laws are always proven false, really, ultimately, etc. Errors from one prediction to another cancel themselves out. That's a very famous kind of notion about prediction, errors cancelling themselves out. And also conditional predictions, what-if predictions. Now, what-if predictions are to really keep the system relatively contained and simply alter odd bits of it and see what actually happens. What if, for example, we build a highway here? What if we actually produce an industrial estate over here? What would be the impact? But even these can be flawed because the models we have to do it are subject to all the problems of prediction, etc. Okay, let me move on and say something thinking about cities. A couple of words about this. Now, cities are complex systems. They're built from the ground up. They're now all local, or global, I should say, and they defy definition. We can't really separate the city from its wider environment. 50 years ago, people believed that if you studied cities as systems, you could define a system, and the system would be relatively active, etc., but sitting in a more quiescent environment to some extent. So the key issue in systems theory was to divide the system from its environment, basically. Increasingly in a global world, one can't really do this. The environment becomes part of the system, and the system becomes part of the environment in that sense. We can't really close them in that sense. The other feature, of course, is that when we think of future cities, we think of grand designs from the top down, but inventing cities is always from the bottom up. We're all involved in it in this particular context. We may not be able to predict in some sense, but we do have control, at least in principle, over what we actually invent. And in all of this context, cities are dynamic systems. A lot of our thinking about cities in the past has been as though they're in equilibrium. Certainly the last 50 years has demonstrated quite dramatically to people thinking about cities that they're never in equilibrium, they're in disequilibrium. They may even be, in systems terms or complexity terms, far from equilibrium in that context. They're not just about space. Geography matters, of course, but they're also about time in that sense. So another point I'll make, and then I'll begin to move on to my particular examples, the high and low frequency cities. So cities are really about dynamics, and we've got to make a distinction between this high and low frequency that I mentioned earlier on. Cities that change fast are high-frequency cities, and cities that change slowly are low-frequency. And these are not different cities. It's just looking at the same city over different time periods. So, for example, the high-frequency city is the 24-hour city. Largely, we've become concerned about this because of the amount of data that is being streamed from embedded sensors, and more particularly, embedded sensors have been taken over by our own personal sensors from mobile phones in this particular context. So vast swathes of data are really being generated in continuing time streams. I'm looking around the audience here. Who's looking? You're all very attentive. I thought at least half of you would be looking at your mobile phones by now. I mean, sort of in this context. But I could see the gentleman from Germany is basically from Potsdam over there. Yeah. But what we're doing all the time is generating information that is being captured in some sense. And that's given us the prospect of thinking about the city over relatively short periods, over high frequencies. I'm not going to say that the data that we get, which is real-time, is any better than previous data. It's richer in many senses, but it's not necessarily any better. In many senses, it's a lot worse because it's largely unstructured. You'll see in a couple of minutes when I got to my first example, when I talk about the Oyster card data set, that there's lots of difficulties with this kind of data set, largely because it's unstructured in some sense. It's not really designed for our purposes. You may not think the population census is designed for our purposes, but it's designed for our purposes much more than the kind of data you get in terms of the real-time streaming from embedded sensors. Okay, so much of our theory in the past has been about the low-frequency city in this particular context. Now, I will talk in terms of a couple of examples about prediction in the low-frequency city when I talk about our national model. Okay, so let me begin with my 4 examples. The first is short-term prediction. Again, to remind you, it relates to transit and real-time stream data. We call it our Oyster card project. The reason why we call it our Oyster card project, it relates to data that we can actually get from automated systems, and most public transport in London, which is my example, operates automated systems where you can tap in and tap out. In the tube system, for example, the underground, you actually tap in and tap out. On the bus systems, you only tap in for a whole range of logistics related to the driver and the control and so on. In that sense, you only tap in that sense. So that kind of data is problematic. But in the tube data, which is a closed system, you tap in and tap out. It's not just the tube. We're talking about overground rail as well. Now, the reason why we're looking at this is that we need to look at we get origin and destination data from the tap-in, tap-out, but we're interested in the shortest routes. If you get onto a subway train at Goodge Street, for example, and you're going to Bank, there are there's lots of different ways you can actually travel through the system in this context. So we're interested in looking at the loading, basically, in terms of what the shortest routes are. We're interested in examining the heterogeneity in the data. Previously, a lot of travel data was thought to be homogeneous, but this data can give us great insight into heterogeneity. We're also interested in demand, which is the tap-in, tap-out data, and we're interested in supply, which is the trains data. We want to tie the two together to look at things like disruption and so on. And what we've done in the London context, we've also extended to a comparative study of Beijing and Singapore, where the subway systems turn out to be fairly similar in many senses in terms of the actual total numbers using the systems and the actual size of the system in that sense. Okay, now here's a picture of where we get the data from. So on the left, for example, you can actually see the tap-in, tap-out system in this context. Many of you may have actually seen this. You can actually use an Oyster card. That's a card you can actually buy over the counter. You can top it up with money. Basically, the system is intelligent enough to actually figure out how far you've actually traveled in some sense when you actually tap out, you've tapped in. You can also use Apple Pay, and you can use a watch basically and tap in that way. That seems to be a bit cumbersome basically when you see people doing this on the scanner. And here, for example, is a mobile phone. So the Oyster card has been loaded onto mobile phone. Interestingly enough, you're paying by MasterCard. And interestingly enough, RBS means Royal Bank of Scotland. It's one of the banks that was the biggest catastrophe in the Great Recession. The British government still own the Royal Bank of Scotland, notwithstanding the fact that the chief executive still gets millions each year in bonuses, basically, but earning a salary which is probably 25 times what the Prime Minister earns, basically. But nevertheless, RBS is still around, but it's owned by the British government. I have a vested interest. Anybody who pays taxes in Britain and lives in Britain probably has a vested interest in this bank. Okay, so that's the tap-in, tap-out data. That's the passenger data. That's demand, basically. And then we have the supply of trains data. All of the trains are basically online in some sense. There's APIs, so you can get this. I'm only interested in the top bit, which is TrackerNet, which controls the positioning of trains on the tube. So this is the data that's used by London Transport, who control the train side of things. Transport for London, I won't get into the differences in the administration, control the passenger side, the network. So the trains data is controlled, and most of this sort of stuff is really designed to actually inform the drivers and the system managers, although some of it is actually poked out onto or pushed out onto the gantries that you can actually see how long a train is, say the waiting time for a train in each of the platforms. So we have demand and supply. One of the things we'd like to do is to connect up demand to supply, and I'll come on to that in a moment. Okay, this is the system that the Oyster card actually pertains to. This is not like your traditional subway map. The subway map is contained within this. Let me see if this has got a little, whoops. Well, obviously that one doesn't work, but oh yeah, here we are. Okay, so this is the circle line basically. You see this abstracted Beck map normally, but this is all the overground rail and some of the network rail where the Oyster card can actually be used basically. But the bit I'm examining is the system of the tube basically, which is this one here basically in that context. So we're just looking at the tube basically. The overground rail could be looked at, although it's a much bigger system. We're talking about a system here which is about 290 stations, basically, and about 4 or 5 million tap-in, tap-outs per day. So it's quite large data. It's not necessarily big by computer science standards in that context. Here's some pictures of taken from a little movie that we made, UCL Engineering made in that context. If you click onto that, I'm not sure I should click onto it. It'll probably, let me just see whether this works. I can never resist clicking on a web link. Yeah, there we are. So you can hear the movie.
I'd come into King's Cross and then travel around London.
Change onto the Victoria line.
Waterloo.
Come off to Russell Square.
I used to probably about once every 3 weeks.
Oh, you can't see it. Don't worry. You can't see it.
We're now beginning to
Probably
log
just as well.
transportation behaviour using smart
Just as
cards,
well.
essentially. We have a very large data set
Now,
which comes
the
from
question
the
is,
Oyster
how do I
card
get out of
system,
it?
which is the swipe card that you charge up to travel
I'm
on
going to
all
need
public
Megan. You're going to have to
transport
tell
in
me how I get
central
out of it.
London.
We've been thinking of ways where we within TfL and our research partners can begin to sort of extract some interesting journey patterns from that wealth of data.
For each day, we had about 4 million of those movements, so to say.
Now we collect this and we have very strong safeguards in place to make sure that our customer identities are protected.
It was a wonderful case for us to really understand how a complex system looks like in a big city like London.
Okay. I knew I shouldn't have done that. Yeah, I know how far we are. Okay, let me... Okay, that's where we were. Okay, so let me show you the kind of data we've got. This is a kind of picture of what goes on in terms of the 24 hours in terms of the tap-in, tap-out data. The two pictures with the red, you can see the morning peak and the evening peak. One of the clear things that we've known for many years is that morning peak is slightly narrower in terms of time and slightly bigger in terms of travel. The evening peak is more elongated, and in the London system you've got a kind of late evening peak as well. If I show you the movie in a moment, and I think I can show you that without actually screwing it up, you will actually see these peaks in a sense. This shows you the entries and exits basically. That's the tap-in data and that's the tap-out data. I'm not going to confuse it anymore, simply to say that there's slight lag. You can almost think that that's the average length of the tube journey, but we're talking here about literally thousands and thousands of passengers. And these are three different subway stations. This actually is Bank, basically, at Bank of England subway station, and it's done in such a way that the morning and evening peaks are separated. This very much looks, in terms of reading these graphs, as though this is journey to work. The one above it is Camden Town, which is north of, just north of the centre, north of Euston Station. That's a very mixed area, a big entertainment core, basically. But the interesting one is the one on the right. Can anybody guess what's happening on the right? So we're 24 hours on the horizontal, and this is the actual flow of passengers in the subway stations. Where is that subway station? Well, it's obvious, isn't it? It's the Arsenal, basically. It's the Emirates in that sense. It's the Arsenal, basically, and the blue is the two Saturday games. This is a synthetic data set taking data over a period of a month in that context. A period of a week, I think, in this particular context. So that's no, it's got to be over a month because you don't have two Saturday games on the same. And the bigger peak is the midweek game, basically. So these are the volumes using the subway station at this particular point. So these are really signatures, etc., that you can get out of the data. And this is a little map of the kind of polycentricity of the subway stations that we wrote the paper when we first got into this, basically, a while ago. Okay, now what we're doing in this particular context, I'm just going to show you very quickly an example of the flows, etc. On the left, we've got the tap-in, tap-out data, and my colleague John Reeds from King's College London, he basically put this together when he was a postdoc in CASA, and he's built a synthetic flow map, really, almost like a blood flow map of the flows on the subway station by linking origins to destinations, where you tap into, where you tap out, using shortest routes. And that's quite problematic in some sense, because if you're a novice tube user, you may not use the shortest route. You may actually, and even if you're an experienced tube user, you may be locked into a travel pattern that is not necessarily shortest route. And we don't know what the shortest routes are from this tap-in, tap-out data. So that's a predictive issue in and of itself, in some senses. So what we're going to see in that context is the 24-hour data, the tap-in, tap-out data over this synthetic period of a week. And on the right, we're going to see the trains data. So let me just click on this. Let me just find the... Okay, and see what happens. Okay, now is that starting? Now the question is, can you see anything really? Okay, you can, there's a little counter there saying, well, it's Sunday based, that's Monday. The morning peak's about to happen. There's the morning peak on Monday, and then middle of the day, and then the evening peak, and then a little blip at the end. You can just see the blip at the end. We're now into Tuesday night, Tuesday morning peak, and so on. And the little blip at the end, the third peak, gets bigger as the week wears on. Because Saturday and Sunday are entirely different because you don't really have journey to work. Now, one of the kind of key features of this data is that it's highly heterogeneous in the sense that we don't really know. What we do know is that only about 10% of people traveling are traveling from the same subway stations in the morning to when they get out, the journey to work, and using the subway station where they get out in the evening and coming back in this particular context. So in other words, only about 10% of the data we can infer and we can't even be certain about that, is related to the journey to work. So there's a vast number of trips in this particular context. Now we've stopped at that point. The other data is the trains data, basically. And I think what I'll actually do is to actually move on to the next slide in that sense. So that's our data in that context. So let me show you the trains data. Now this is the data with the trains, and there's a number of interesting features in this particular context. When I first saw this movie, and this is taken from the API, we've got a guy in our group who's collecting this data all the time, basically, and archiving it from the API. I said to him, Richard, in the visualization, can you get the trains back on the tracks? Basically, some of those trains on that looks like the Metropolitan line, that purple one, are coming off the tracks in that sense. So he said, Mike, he said, you should know the answer to this. He said, this is a big data set. I could get the trains back on the tracks, but it would take me 1,000 years. He said, I would have to pick up every individual train and put it back on the line. And what this is noise. TrackerNet is a notoriously bad way of recording in that sense. That, in other words, these trains are not on the tracks because of the noise in the system and the way it's actually built up in this particular context. So it's an interesting example of the limits to big data in that sense. Let me just show it again, because you can see, in some sense, TrackerNet being reset. Let me go again. TrackerNet resets itself basically at about 9 o'clock. In other words, it goes down basically and it distorts the data. Now the key issue is we're very interested in connecting up the tap in, tap out data to the supply data, the trains data, because if we're interested in disruptions, we want to really know what person who's tapped into the system gets on what train, basically. Because if I'm in Bank, if I'm in Bank Station and I have to go to the Docklands Light Railway from coming in on the Central Line, I know exactly where to go to. But if you were in Bank and you'd never been in Bank before, you could spend half an hour wandering around and finding the Circle Line and all this sort of business. So in some sense, it's important to know in measuring disruption for passengers what train the actual passenger gets on. Now, Wi-Fi is being experimented with on the tube. There's lots of restrictions on the tube. You can't drink alcohol. The Shadow Home Secretary basically has just been, somebody took a photograph of her swigging a tub of some sort of alcoholic drink on the overground, basically. So that came up in the popular press the other day. So you can't drink on the tube. You can't take photographs. You can't use Wi-Fi. If you are able to use Wi-Fi, there are 1 or 2 of these clubs around that enable you to use Wi-Fi in some sense and connect to various systems who are monitoring you in that sense, but you have to sign certain conditions, and so it's very restrictive in terms of tying up what train you get on to where you actually tap in. So eventually that problem will be handled in some sense, but there are so many difficulties in terms of connecting it together that it's quite problematic. Okay, let me move on. Now, very quickly, we've looked at some data in Beijing. I'm not going to labor this except to say that all of this kind of analytics really relates to the fact that the London tube is a much more volatile system than the Singapore and the Beijing tube systems in that sense. So, for example, this is largely due, we think, to the fact that the London system is very old. If you're at Victoria Station in the London Underground at the peak hour, for example, very often, at least twice a week, Victoria Station would be closed and people would be queuing up to get on the tube, basically, because it simply can't handle the volume. That's partly a capacity issue. In Beijing, they tell me that in Beijing, people actually queue up very orderly to get on the tube there. But it's also due to the fact the system is more recent. And in Singapore, well, well, you could draw your own conclusions about Singapore, but people are extremely well regimented in Singapore as well. But it's really not to do with human behavior. It's more, I think, to do with the fact that the systems are different in terms of capacity. Okay, some of the things we've been doing in that context, and I'll whip through this so I can get on my second example. This is a case in 2012. The biggest data set we have from Transport for London is the 3-month period in 2012 over the time of the Olympics. They donated this data set to us. Again, it's quite tricky to get these data sets, but you can. They're in the public domain. Sorry, they're in the domain for academics if you sign the various conditions and so on. But this data set was given to us largely because Transport for London didn't have the capacity to analyse what happened when 1 million extra tourists came into London associated with the Olympics in that sense. In fact, the system worked fairly well. It was fairly adaptive in some sense, but it was also accompanied by a lot of instructions about take your holidays during the Olympics, etc. You know, some firms were decentralized and so on. So this was within the data set on the 19th of July from 10 to 8 in the morning till 4 minutes past 12. That's quite a long time, 4 hours. This particular line was actually down, basically, and that's almost unprecedented to get that kind of disruption. In fact, we can calculate from the data that 1.23 million Oyster card holders were actually disturbed in terms of their travel. And we have a whole set of analytics that really relate to increased travel time at each of these tubes. You could probably say, although we didn't test this exactly, you could probably say that most of the 1.23 million persons would be disadvantaged in terms of travel time by the fact that this particular critical loop on the central line was down, largely due to the fact of comparing the amount of travel time under normal conditions with the amount of travel time in these stations in this particular context. Okay, so let me move on to thinking about another kind of prediction. We're talking here about short-term prediction and the difficulties of doing this. Now, we're also working with Airbnb data for London, which is available from 2008. That's when Airbnb was established. I think 2007 the company is set up. And the problem with the data we've got, and again, this data is available from the appropriate API. The problem with the data is that it only ever gives us a snapshot of the dynamics of the cross-section in time. Now, anybody who's worked with dynamics data knows these sorts of problems. That, in other words, the snapshot at a particular point in time can often miss what's happening between the times when the snapshots are changed. So if I've got 2008 data and then 2009 data, some Airbnbs may have come and gone in that period and we're not actually picking them up. That's true of all migration data. If you think of census migration data, actually not quite. In the British census, they do ask the question specifically about where you were back in 1991 or 2001 or 2011, whatever. So you have a slightly better digging down into the nature of migration. But lots of dynamic data simply miss what's happening between the snapshots in time. This is very true of the Airbnb data. Now, the project that our PhD student, Zara Shabrina, Zara is looking at a project which is really looking at the location of Airbnbs relative to different attractions. She's more interested in a kind of gravitational type spatial interaction model linking where the Airbnb customers are, clients if you like in that sense, to the kind of attractions which they visit. But as a byproduct of this, it's very clear from her data set that the Airbnb in a context like London is having an enormous impact on the housing market. We're talking about a housing market here that is extremely tight. The average rental per month in London, and about 40% of people are renting in London, the average rental per month is something like £1,800 a month. That's the equivalent of, let's say, $2,500 a month, and for that you'd probably get 2-bedroom flat, basically, in that sense. So it's a very tight housing market in that sense. It's much compounded by the fact that London is a place where there's a vast number of people who are there temporarily because of the EU They're not even migrant workers, they're just people from all over the place within the EU who are there, and that's true of Paris and other places as well in this context. So you've got a tight housing market, very high prices, very little housing being built over the last 20, 30 years, etc., for a whole range of other economic and social reasons in the UK. And Airbnb is reducing, we think, that particular housing market. So we're interested in actually predicting the extent to which the housing market is being affected in that sense. We really want to answer the question, how much housing has gone to Airbnb, which might have been available for ordinary tenants in this particular context. And to answer that question from this sort of data is quite problematic in that sense. Oops, sorry. So these are just pictures, in fact, of, this is pictures of the growth of Airbnb from 2008 to today, basically, in that sense. There's a bunch of attractions in the top. You can see that Zara is interested in tying up the locations of people in Airbnb. This is the density with the attractions, so that's a main part of the thesis. But as byproduct, we're interested in doing some analysis of the impact on the housing market related to the provision of Airbnb. This is the density of Airbnb, basically, in that sense, tying that to actually different housing types in this particular context. And the next slide gives you an indication of what she's been doing. These are different flat types, apartment types, basically, conversions, commercial and purpose-built, all flats basically. Commercial are changes from the commercial sector into flats basically, so you can do that without planning permission these days, the movement from offices to residential in that sense. These are purpose-built flats, and then you've got conversions in a sense. So what she's done is a whole variety of different fancy spatial analysis basically, entropy, all that kind of stuff. But what we're really interested in this context is saying how much of that Airbnb is taking away in this particular context. And the interesting thing is that we can correlate Airbnb with different housing types, tenure types, etc., in these different areas. But what we don't know is the answer to this question about how much. And short of actually asking anybody the question, would you have rented in this Airbnb as opposed to what you might be renting? In other words, asking people a question, and even in a person trying to answer that question, it's still extremely problematic. It's a hypothetical question in that sense. So to actually answer the question, we can only really just look at the data and produce kind of plausible explanations in that sense. So limits to prediction in a sense, and difficult to know how one would actually tackle that problem, but it's a very important problem in terms of regulating Airbnb, and there is substantial regulation of Airbnb. You can only rent up to 90 days, I think, in the London context, and different cities have different regulatory regimes. Okay, so that's my second example. My third example is a little bit more technical in some sense, but it's really an issue that I raised at the beginning that is posed in this notion of, can we use the data much more effectively in making predictions than actually building traditional models of the data? We never really used the data back when I began in this area because we always thought that models were much more appropriate. What we wanted to do was to explain the data. We didn't want to actually use the data to actually enable us to make the prediction other than actually validating a model, getting a model to actually reproduce the data in that sense. And the reason for this was we were interested in how the world worked, basically. 50 years on in my context, we know that it's extremely difficult to make good predictions. I said earlier on there wasn't a good catalogue of successes and failures. In some areas there is. In transport modelling, for example, there's been quite a lot of work done which generally comes to a very pessimistic conclusion that most of the examples are predicting adding a new highway, building a model to predict how much traffic there'll be on the new highway, and then looking at how much traffic there is on that highway after it's been built. Most of that data leads to very, very bad predictions in that sense. So we kind of know, really, that in some senses our models are very bad predictors of this particular context. So can we begin to think about using the data more effectively. So if most of the future in the short term is a function of what we see in the present, then maybe the best model we've got to predict the future, again over the short term, is to actually use the data that we have in the present, or at least to begin to model the differences of dating the data. So this, for example, and the reason why I have time going from right to left, basically, is that when we write our equations, we have explanation on the right-hand side and what we're trying to explain on the left-hand side. So data then and data now. So this is typically the notion of modeling close to the data. In the middle there, we update the data. One way of thinking about it is data then and data now. Some kind of mechanism for updating the data, basically. That mechanism might be modeling the data, etc. So modeling the data in a very different sense from building a model of the data in this context. And it could be seen in this context as a kind of Bayes equation. So in this particular context, the model that I'm going to illustrate to you in this particular context is based on this. So very quickly, I won't let you get away with no equations, actually, so we'll just have a few equations, but basically you can sort of miss this bit. So here's the stuff on the right. Tij is the traffic pattern that we see now between origins and destinations. That might be John Reed's traffic pattern for the tube, okay, in, let's say, July 2012, Tijt, and Tijt plus 1 might be the same traffic on the tube in 3 months later, basically, in September, in this context. And all that machinery in the middle between the data then and the data now, or the data in July and the data in September, is the kind of machinery that will enable us to build the model. We can say something about the origin and the destination. We can say something about the actual link between them in this context. So data now and data then, so model in the middle here, etc. So we can write that in this particular way. There are all the various bits of it. And if you actually cut out the link in terms of the the IJ flow in that context, then you end up with a model at the bottom here, which was first introduced in 1953 for limited traffic forecasting, where you took the existing trip distribution and you simply updated it to the observed the new trip distribution by changing the scaling factors, basically, in a sense. So this is really a model close to the data. Now, the issue here, of course, is how good is this way of actually predicting Tij t plus 1 from time t compared to building a model of Tij t and using that to predict Tij t plus 1. And in all the exercises, all the case studies we've looked at, then I'm just going to whip through this very quickly. Then in all the examples we've looked at, this is a much better way that using the data to predict even 10 years ahead is a much, much better way than actually building a model of that data, spatial interaction model, that we have always assumed in the past are quite good predictively. We have R-squareds and goodness of fit things which are at the level of 70-80%, something of this sort. But in terms of using the data, we can get much better predictions, etc. So let me just test this in terms of a simple example. This is Britain, basically England, Scotland, Wales. And this is the GLA. This bit here is the Greater London Authority. That's quite important. This is the outer Met area, which is really London itself, basically. But this is the GLA area. About 8 million people live in that. If you go to Wikipedia and ask and key in population of London, they give you this, basically. But this bit is just simply shows you the difficulty of drawing the boundary. We're really talking about this. This contains all the London airports. Oxford and Cambridge are on the outside of this, but arguably Oxford and Cambridge should be parts of London. It takes 40 minutes on the train to get to Oxford, about the same to Cambridge on the faster trains. So in some senses, what we're doing is to take data from this. I'll come back to this because this is relevant to my final example that I'll be talking about in a moment. Now here for example, says it all. This is a very crude example. It's a fairly coarse level of resolution. These are the London boroughs, all 33 of them. That's employment and population in origins and destinations in 1991, and then the change in the employment and the population basically in this particular context. Bigger change in total for the population, I think, in terms of its distribution than for employment. That's the trip pattern. You can see the difficulties of visualization in this context. It's a very small problem. Think about visualizing that for 10,000 zones. There's 33 zones here. And that's the issue about the model that we're going to come on to. Lots of ingenious ways of thinking about how to visualize. These are the London boroughs, the zones basically, and these are the flows inside of this, and these are the flows across, so-called circus diagrams, circos diagrams in that sense. And what we've done is to actually take the journey to work data in 1991 and update it to 2001 in this particular context. So this is the predicted data. And when we actually graph that data, essentially we get a very high correlation. So we're taking the data that we observed in 1991 and making a forecast for 2001 simply by updating the data in that sense. And we get a prediction which is, well, to all intents and purposes, 98% of it is actually explained in this context. Now build a spatial interaction model of the 1991 data and use it to predict 2001. And in that particular context, the R-squareds or the correlations are not an order of magnitude, but considerably smaller in that sense. We're only really accounting for about 70% of the data. Okay, I simply leave you in this context to say that this is a way of thinking about a minimal kind of prediction in this context. And what we want to do is to take this kind of thing and actually, instead of running our national model, actually using a data-driven version of it. But I'll come on to that in a moment. Okay. Right, long-term prediction. How are we doing for time, ladies and gentlemen? I've not been following it. 7 o'clock. So I start at 6? Oh, right, okay. Well, a quick rundown on the on this quant model. Quite visual in some sense. Let me tell you about it. We're building a model for the UK based on small zones, the kind of things you've been seeing in this context already. Small zones, divided Britain, we divided England, Scotland, Wales into, actually it's not 10,000 zones, it's actually something like 8,417 basically in that sense, but it's still pretty big. 8,417 squared is like 65 million, so trip matrices of 65 million. You're in shortest route problems on these sorts of things and takes time. Anyway, the models which are running, and we have quite an elaborate residential housing model running in that context. It's built on 3 modes, public transport, basically bus, rail and road in that context, in this particular context. The model runs, it's web-based, it runs in about 30 seconds basically. 30 seconds is too fast. That uses a whole variety of fancy GPUs and all sorts of things, etc. And it's getting faster literally day by day. We could, if we could afford it, get really fast computers and probably get it down to about 15 seconds basically. But if you're a user sitting at a terminal trying to use this basically, you're not really wanting to even wait for 15 seconds. You want it instantly, etc. Okay, so we've got a long tradition of different models, etc. I'm going to go through these very quickly. This was our climate change model for Greater London. This basically is dividing London into 633 zones. That's Heathrow, that little red spot. Heathrow is a very big hub. About 250,000 people work in Heathrow, in and around that area, Hillingdon. And a lot of people who work in Heathrow really come from Reading and Maidenhead and Slough and places to the west of here. And in some senses, this is a completely artificial boundary. That's the whole point. My first point was, you know, the system and the environment are colliding because of globalization. This is a classic example in this particular context. That's what the travel pattern is like in London. 38%, this was in 2011, 38% of people travel by road, 12% by bus, 12% by heavy rail, 19% by light rail. We've included tube as light rail. Tube is not strictly speaking light rail. It's actually heavy rail. It was originally heavy rail when tubes first began. And then about 90% are walking and biking. So that area with 8 million people, only 38% of people are traveling by road. That means car. And basically, most of those people are out in the suburbs rather than towards the centre. Okay, now, lots of things we could do here. This is just giving you an indication of the visualization of these things. This is an accessibility map, and the blue represents low accessibility. It's based on travel cost, and the red is high accessibility. Why is the centre of London low accessibility? Because if you cross that boundary, you will be charged £12.50, basically, which is the congestion charge during the working day. The congestion charge, so this is travel cost, basically, accessibility and travel cost. In fact, I should tell you the story that the Mayor of London has just introduced the ultra-low emission zone, which is this zone here. It's going to extend out to the more of the red next year. The ultra-low emission zone works 7/24, 24/7, and it costs you, if you don't satisfy certain criteria, it costs you £12.50 a day. So me having a 2005 diesel car, basically, pay £12.50 a day for the ultra-low emissions charge and £11.50 a day for the congestion charge. So to get into central London to my house, to my garage, basically, under the flats, it cost me that amount of money. So basically, I've driven my car out of London a couple of weeks ago and to my house in Bath, and there it will stay. I don't want to pay the £12.50. And it's working, right? He's got rid of one car, basically. And the reason is that every diesel car which is older than 5 years old, and every car any car which is over 10 years old have to pay that charge, basically. So that's pretty draconian, right, basically. But that's the nature, and it's all to do with pollution. Okay, now I didn't really want to tell you that, but these are pictures of what goes on in this context. We have quite a lot of experience of building web-based interfaces. I want to put this on very quickly. We're also involved in using as much data as we can get out there, and this is something we did with the Future Cities Catapult for Dubai very quickly. We built this similar version of the models we've been building for London for Dubai itself, and we did this in about 3 or 4 days, basically. So on the Dubai statistics site, you can actually have a map like this, and you have population, etc. Most of this, I believe, I've never been to Dubai, most of this is basically desert. All the kind of action is along the coast, basically, towards the top, which is the sort of city centre. The data, one of our programmers basically reverse engineered and got the shapefile out of this. I don't know how he did it, but he did it. I mean, so he got the shapefile. I did register with the Dubai Statistics Authority because they said they'd provide you with all this data and so on, sent them some emails. And we were supposed to be doing this for the Dubai government, basically, but although they periodically send me, you know, a Christmas card, that sort of thing, on the Dubai thing, I never got any data out of them. So all the data we got, we scraped off the web, basically. So in other words, this was data from Google Places. Dubai built up area from the satellite imagery, Landsat 8, and various things from OpenStreetMap, etc., Dubai, business diversity, and so on. So we built our data set really rapidly because all we wanted to do was very quickly do a proof of concept. So there's enough data out there to build a very minimal sketch model. And this is the interface, and I'm just going to go through this very quickly. This is the kind of thing you would get if you run the desktop model. Now, what we want to do is to scale this model up to Britain, basically, in that context. So that's what we finished up with on Dubai. So we're quite confident that we could build very quick sketch planning models to get a sense of even just organizing the data from data that we could get on the web. Okay, now let me tell you the last thing. I'll spend 5 more minutes, and I appreciate that I've run over time a little bit. But nevertheless, what I want to do is to say we've now got Scotland into this England and Wales model. We have this zonal system, this census geography called middle layer. They're called output areas. They're a bit like what would output areas be, Stuart, in terms of blocks here, or Pardon? Enumeration district is the new name, output area is the new name for enumeration districts in the UK census. But I'm thinking of how does it compare to, it's around about 300 people, basically. These MSOAs, middle layer super output areas, are about 7,000 people. So out of 60 million people, we've got something in the order of 8,500 of these areas, basically. Now, the model works, it's 3 modes, as I mentioned a moment ago, and it's also built on the basis of very detailed transportation networks. If we alter any transportation thing, we're altering it at a much finer scale. The rail network is pretty sparse, not much rail left in Britain, although a hell of a lot compared to here. The road network is very detailed, 8 million segments, 3 million roads, that's the Ordnance Survey master map, and the public transport network is put together by various kind of Google kind of traffic things and some Google kind of technology to do that. Okay, so I'm just going to go through this. So this is Scotland being added in. Basically, you can see the previous slide shows, this is the way we actually show the journey, show the flows. We use a vector field. So these are averages of the flows, basically, etc. You can see we've added Scotland in the next one, basically, and that's fairly typical of what you would see if you ran the interface. You'd load, basically, and begin to explore the data. Well, run the model, of course, but also explore the data at this level and zoom in this particular context. So let me give you, that's the kind of the architecture of the system. So it's our programmer, Richard Milton, who has worked for us in CASA for a long time, he thinks of this as really a set of web-based services, basically. But essentially, this is the kind of server side, and this is the client side, and there are various fancy ways of putting stuff on the server side and moving it to the client side and so on. Some quite technical things in terms of making this work as fast as possible. Okay, so if you log on, this is basically what you get, basically. Now, it's buyer beware, proof of concept, and all that kind of thing. We've got a lot to do on it. This is the England and Wales model. You get some pull-down menus. These are just pictures, and you can pull it down and zoom in that context. So this is observed population in that context. As you zoom in, this is an example on a very slow link where you actually see Mapbox basically producing these tiles, and that's the kind of picture you get. This is the green belt. These are the green belts, basically. That's map accessibility. These are all in the package. So you can explore the data, which I've just been showing you. You can also run the model, basically, and running the model, and then you can begin to look at scenarios. Okay, so running the model only produces for you basically what we've seen in terms of the data. So the similar things to see how good the model is. But then it comes into its own to some extent when we start talking about scenarios. So let me give you an example of a simple scenario. This is West Lancashire, which is the Wirral and Merseyside, Liverpool, basically. And the reason why I chose this is because in that red spot, basically, that's where I was born and brought up. And so I have, by the way, for accent connoisseurs, my accent is, don't say it, Stuart, your accent's Newcastle, right, Middlesbrough. But my accent is what you would call mildly Liverpool, okay, with tinges of West Lancastrian, right? Anybody from Liverpool would be able to pick me up straight away, but it's not really a hard Liverpool accent. The Beatles were harder than myself, and some of the Liverpool accents are almost Irish, basically, a mixture of Irish and Welsh. Okay, so what we're doing in that particular area is putting in 40,000 jobs, and what the model will do, it'll predict where the population lives in this particular context, and shows you pluses and minuses in terms of increased accessibility. So nothing very fancy about that, but actually happening before your eyes in that sense. And anybody who really wants to test one of the scenarios can actually do it in that context. Now, this is where, to some extent, the thing comes into its own. What I'm going to do is to show you some impact analysis to the reason why this model is particularly useful at the present time. This is Crossrail, Crossrail is, well, it's the biggest infrastructure project in Europe, basically, in terms of billions of pounds, billions of euros, basically. But it's a high-speed tube line running under London from the east in Shenfield, taking in some down towards Greenwich and Abbey Wood. The red bit is the underground section within London that really runs from the Olympic Games site and Abbey Wood all the way through to beyond Paddington. That's the Heathrow Spur, basically, and it's all the way out to Reading. It's going to have one train every 2 minutes whenever it opens. Keeps being put back a year, basically. If you go to central London, you'll see massive redevelopment of Tottenham Court Road, Bond Street and so on, these new stations being built. The advantage that I've got is that if I live somewhere in the city here, and I will be able to take a train all the way to Reading and then change onto the Great Western Line and go to my house in Bath, basically, very, very quickly, probably cutting half an hour off my journey, basically. So one of the kind of key features is what happens when we put this line, we change the transport time, travel time on the route, we plug it in and we look at the impact, basically. Now this shows you the improvement in journeys. We can work out all sorts of indices in terms of the rail network, the improvement of journeys in that sense. This is the population change for the rail mode only, associated with just people who are switching to rail and where they traditionally lived, the increased numbers. And this is the population change all modes. Imagine that we have population modelled in London here, and we put the line in. Nothing else changes apart from the fact that people adjust. Some people move to be nearer the rail line and use it in that context. Other people will be displaced further away in that particular context. And also there's the modal split issue, because we're talking about a rail line on top of a related to the road system and the bus system in that context. So a number of quite complicated things actually happening, basically. It's a classic what-if type scenario. And you can actually see that these are the kind of displacements that take place. And of course, if we blew this map up to the whole of the, well, we can see it in a wider context in terms of this. There are even impacts in terms of population growth into East Anglia here in some sense. So this is the reason for thinking about the whole lot in a sense. Now I have lots of other scenarios I could show you. High Speed 2, which is the fast line from London to Birmingham to Manchester, and then into High Speed 3 going up to the West Yorkshire, Leeds, and up to Newcastle, basically. Here, for example, is a proposal we did for the Combined Authority in Manchester. They wanted a new fast rail line from Wigan North Western through the central Manchester and then down to Manchester Airport in that sense. So we plugged this into the model, basically. And this is the scenario thing where we've changed all these travel times, travel times, I should say. And these are the kind of impacts that take place. Last but not least, here is an example of putting in a high-speed line from Glasgow to Edinburgh. So we've given that 20 minutes. And this is the impact in terms of travel times, travel time changes, basically, the number of seconds saved on every possible trip from any origin to any destination once we put this line in. And there are impacts further afield. The reason why we get changes here is that the rail system, it's a fairly coarse network compared to roads and so on, but the rail system actually impacts on these different places. Okay, right. So, and also I should say that, that this particular project was originally funded by the Future Cities Catapult, which is a government agency, but has found use with the National Infrastructure Commission and the Infrastructure and Projects Authority in the Treasury. Okay, where do we go from here? Let me summarize very quickly. Lots of things about prediction in this talk. We need to use data much more. This is one of my conclusions, to build models that are closer to the data. And there are theories about the data and changes in the data reflecting temporal dynamics. So that's one point I think that I'd like to sort of take from this kind of work. The other feature is that we need to build more than one model. It's very clear now that, I mean, this is a very long-standing notion that if you have a problem and you build one model and only one model, then that's a very limited thing. So the idea of building many models from different perspectives of the same phenomena is something that I think we should take seriously and explore. Some of the problems of prediction will still be there, basically, but nevertheless, this is part of the notion of exploration. We need to develop new insights in terms of thinking about how to use models for prediction to actually inform the debate in that sense, and we need a science of prediction. So far, we've really just got straws in the wind, basically. We almost need a new science itself, which puts validation, verification, hypothesis testing in its place and elevates the role of invention. And last but not least, we can only do this collectively. This is not something that can really be done by us, but at least we now have the media to begin to do it in terms of kind of web-based thinking. On that note, I'll stop. Here are some things that we've written at different things. Let me just refer you to the Airbnb, which is the most recent thing, which is on the archive. That's the physics archive with Sabrina Elsa Arcaute, one of my colleagues, and myself. And then we did an issue on big data in the city in the journal Built Environment, so various names here, sort of Colorati, John Reed's, various people, and so on. And then all of these other bits. So I'll leave you on that point and hand it back to Tristan.
Much better than fitting the gravity model or spatial interaction model in 91 flows and then running that on 2001 without knowing the 2001 flows. So that doesn't seem surprising to me at all.
Of course, the acid test would be to take the 2011 flows.
Exactly.
Yeah.
Exactly. So, yeah. And have you done it?
Well.
As the 91, if you model the change from 91 to 2001 and use that model to predict 10 years ahead, does it do better than a static gravity model fit to 2001?
Okay, we have done that, okay. We didn't include it in this because when we did this, basically the 2011 census, it was 2014 we did this, the 2011 census results hadn't been released for those particular flows. But we have done it subsequently, and we've actually blown it up. And you're absolutely right. I didn't report it because basically we've not written it up in that context, but we were getting correlations of something in the order of about 0.92, etc. So in other words, and I probably should have also said that when we look at the amount of change in the origins and destinations, that's really quite substantial. We're talking about a 30% change in absolute volumes of trips overall, basically, which is employment, working and living employment, between 91 and 2001. Quite big. Less between 2001 and 2011, something in the order of about 15%, basically, at that point. And that reflects, basically, the growth of employment in London, simple as that. But you're right. I mean, the acid test of even a database model like this is to then find a situation where the model could be said to be independent. Even the model of this updating is then independent of the thing that you're actually predicting. Because that's true of any model. And in Lowry's little paper back in '65, he said that the acid test, this was before anybody did any of this stuff, of course, the acid test of a model in this, a model in any area, is to actually fit the model to, Phoenix, and then take it away and see whether it works on Los Angeles. Well, frankly, you would be mad to do that because you know it's not going to work. There are so many differences, right? And to some extent, I've not talked very much about that, but that's a major issue too. How replicable is the model, or transferable is the model that you've actually got? because of course science is based on the notion of generalizability and transferability and so on.
Well, we need to get Mike to dinner, but he's going to be here for a few more days, so please join me in thanking him, and I hope you have another opportunity.
Thank you.